My name is Matthias. I'm going to talk to you about graphs. But before I get to that point, I want to start with a story that starts way, way back. As a teenager, I read a book about a teenage boy who found himself into all kinds of adventures, mysteries, where he had to solve a bunch of puzzles in order to figure out what was going on in his village. It was kind of like a Sherlock Holmes, but for kids, and without that superpower intelligence. He was a smart boy, no doubt, but he was just above average smart. However, he did have a tool, and that was a book. It was a magical book that his father had given to him just before he disappeared. And the boy took notes diligently in this book, writing down every piece of information that he thought would be useful later on. And then when he was confronted with a puzzle, some sort of cipher or code word, something he had to come up with, he would take the book, drop it into the palm of his hand. It would open at the page where he had written down the information that he needed in order to figure out what to do next. I thought that was a genius idea. I wanted to have that book. In particular in school, I wanted to have that book. See, my memory is pretty bad. I mean, I'm doing well with numbers, but when it comes to names, like names of places, people, events, it's just horrible. I mean, it just completely escapes me. When the teacher puts you on the spot and says, hey, you go name the 4 bones in the human inner ear, I'm like, I have no clue. I think it's pretty cool how it works, but I don't know what the bones are called. Nor did I really think that was very important. So I wanted to have that book. Now, I didn't have a magical book. My father never disappeared. So I stole one of the notebooks out of his drawer and started taking notes myself. I was kind of overambitious at first, writing down every single thing that happened to me, which was socially very awkward. So I toned that back a little bit and kept writing notes. However, it was then that I realized what the real magic was all about. It wasn't that the book seemingly had an infinite number of pages where you could write stuff on. It was that it would always open at the exact right page. See, when you write notes, you write them, and then they're somewhere, but you never find them again. And that's exactly what happened to me. I would write notes, but I would never find what I was actually looking for. And so I kind of gave up on that whole idea for a little bit. I figured I should find a subject that had the highest thinking to memorization ratio. So I ended up studying mathematics. But I never could really let go of that idea of the magic book. And I figured, man, there should be a way that we can build a tool or something that does that so that we can finally get rid of having to memorize stuff, right? Useless stuff mostly. And so I figured the best discipline or the best skill set that would enable me to do that was probably computer science. So I switched over from mathematics to computer science. Now, I have to burst the bubble right up front. I never actually build a magical book. Or actually I haven't built it yet, hopefully. But it was a quite interesting journey thus far, and a journey that I want to talk to you about today, because I think it helped me appreciate what that problem was really about. As I later learned, it was called contextual information retrieval. And I learned a lot about the problem, but more importantly about that class of problems. And I think that would be very useful down the road and in the future as we're more and more confronted with this class of problems. So when I switched over from mathematics to computer science, went to grad school for computer science, I was generally pointed in the direction of artificial intelligence, machine learning, natural language processing, information retrieval. So the lines between those are pretty blurry, but that seemed to be sort of the area that I wanted to get into in order to solve that problem and build the magical book. When I looked at those, I was like, holy cow, they have done so much research on that already. Right? That's like kind of the grad school shock when you go in, you're like, wow, every single problem has already been solved, I'm screwed. But then again, it's like, well, they've done all this great work, but here we are, and we're still using keyword search plus for information retrieval. So what's going on? Why haven't we done a lot better? Why haven't we built this intelligent machine yet that allows us to do all these cool things? And most importantly, not having to memorize anything. I think, retrospectively, there are 2 reasons for that I want to talk about. The first reason being that in artificial intelligence, machine learning, or those disciplines, you tend to work with abstractions. You tend to model the world. And we're all familiar with that. I mean, everybody who has ever touched a program or ever written a program knows that what you're essentially doing is you're trying to find an abstraction for the world, a representation for the world. And when you do so, you're basically making some assumptions about how you want to represent things. Now, until we have reached that point that people call the singularity, and here it's coming, until we have reached that point, there's still humans in front of that machine that need to interact with it. And whether it's formal logical languages in AI or the vectors that machine learning appreciates, it's still the case that for us humans, we have a different way of thinking about it. And so I think the first thing that started to sort of dawn on me was that we needed a way to better enable humans to interact with these things that we're building. And so looking at neuroscience, one of the things that I found was that in neuroscience, people have found out that humans think associatively. All right, that's probably not news to anybody here. The way we think about things, the way we store things in our brain is associatively. So things like associations we are very familiar with. We store things within context. That's why we are so excellent at contextual retrieval and contextual reasoning. However, in computers, we don't do that. And I want to sort of, do a little experiment here. Since we have a lot of humans in the room, I figure we do a little experiments to demonstrate that. And I brought two queries that I want you guys to have a look at. The first question here is, what is the name of and the highest degree earned by the wife of the current president of the United States of America? Anybody know?
Michelle Obama's loss.
Exactly. Michelle Obama, and she has a JD. Now that took this gentleman really a couple hundred milliseconds at most, plus he had to read the question, so that puts him at an unfair disadvantage compared to a computer. But let's look at this from a computer. Because what's really impressive is that he just solved a four-way join. Yeah, I hear a lot of pain in that laughter because anybody who has tried to solve four-way joins on large tables knows how painful that can be. How much tuning has to go into this, right? I don't think he'd tune. I hope you didn't take any drugs this morning. But the point is, if you try to do this on a relational machine, assuming you have a table of all humans in the world, of all presidents, of all countries, of all the degrees that these people earned, you have a hell of a job to do trying to optimize that thing. Yet here we have somebody who has a brain that operates on just a merely 20 watts, and he did that just like that. All right, let's do a different query, and this time I'm going to take a little easier on you guys because I don't want to wear you out. So let's look at this one. What is the average term length of those presidents of the United States that took office in the 1980s or later? In years. 7 years? 6? 8? Anybody else? Wow, so now we're doing binary search? So that's what we're gonna do? It's actually 6.6, guys. And it was a stupid, simple one-way join. What's going on? The point of this exercise is really to show that while this query is really easy for a relational database or a tabular database, it turns out to be quite difficult for humans. And the other way around, the query that we just looked at, which is quite difficult for machines, in particular at scale, turns out to be pretty easy for us. So somehow there's something going on. There seems to be some sort of an impedance mismatch between the two. And that's really the point of this exercise is to point that out, that the way the abstractions we have chosen to represent our data are not very natural to us humans. Right? I mean, if I look at my database class, all we ever talked about really was relational databases. So that was the world for us. That's how we thought about data, right? There was really nothing else. I mean, there was sort of this brief history on databases kind of thing, like, look what those guys did, and now we have found the golden solution, which is relational database, and then we're going to stick with that ever after. But the thing is, for humans, that doesn't seem to be the case. We store things associatively, and a representation that seems to make a lot more sense to humans is that of a graph. That seems to be a lot closer to the way that we intuitively think about information, the way that we represent information in our head. Now, we use neurons and axons and dendrites and all these things. That's our hardware. But at the abstraction, at the representation layer, these seems to be awfully close to what's going on in our head, and seems to be a much better representation to bridge the impedance mismatch that is going on here. Now, for those of you who aren't familiar with graphs, and it's really more or less the fault of our education, we really don't talk about them that much. You might have to do a minimum spanning tree here and there, but that's about it. A graph, at the core, really only consists of two atomic elements, and those are vertices and edges. Vertices in this particular representation are shown as circles, and edges are shown as arcs between those circles. Edges are directed to indicate the directionality. So, for instance, we have an edge between Barack Obama and the United States of America, labeled president, to indicate that Barack Obama is indeed the president of the United States. Furthermore, vertices and edges both have properties on them. Those are indicated by these white boxes. Properties decorate vertices and edges to give them more meaning. For instance, the president edge that I just indicated has a box on it that says he was president from 2008, and the until box is empty because he's still in office and therefore still the president of the United States. For previous presidents, we have an until date indicating that they're no longer president of the United States. There are further family relationships encoded in this graph, like spouse and father, as you can see, and we have captured the degrees that Michelle Obama has earned in her career. Now, with that representation, once you get used to it, it's actually quite natural. And it's a very expressive representation for the kinds of information that we're typically confronted with, because it allows us to have an arbitrary set of elements or entities represented as vertices and then capture any kind of relationship that might exist between those by edges, which makes it very flexible. It also gives rise, so this is on the representation side, it also gives rise to means of querying this data or analyzing this data that is much more natural to our associative way of thinking and this graphical way of representing data. The query language that I want to talk here about today is called Gremlin. And we're going to look at the very same query that this gentleman up front just so eloquently solved, and that is that of, who's Michelle Obama and what's her highest degree. And you can see that in a graph, it actually operates like you would think about it associatively. We start with the United States of America. We traverse out, so this is G.uppercase V. The language, is probably new to most people in the room, but I think after you stare at it for a little while, you get an intuitive hang of it. We start with the graph G, so we have an identifier for the graph. Then we say, give me all the vertices of that graph. That's uppercase V. But I only want to have those where the country name is the United States of America. So I'm restricting my initial vertex set, which then boils down to an index retrieval on the graph. Then I have identified the vertex USA, which is all the way to the left up here. And starting from that vertex, I then start to traverse. So what I say within E is that I want all in edges that are labeled president and then does not have an until date. Right, so thereby I identify all edges that indicate current presidents of the United States. I then retrieve the outgoing vertex, so the vertex at the other end of that edge, which is Barack Obama. I then say, who is Barack Obama's spouse, following the spouse edge in the out direction. I indicate that to be my variable x, which I can then later use to either further process it or retrieve it. And then I say, from that point on, I want to follow the degree edges, so I want to look at all the degrees that Michelle Obama earned, following the out edges according to the degree label. I want to retrieve the highest one. Since I have implicitly ordered those, I just have to retrieve the first, select that as Y, and then get its name to determine that it's a Juris Doctor. So you can see how this retrieval here doesn't use any joins for ones, but secondly also really mirrors the way that you would internally think about it. Right? If you follow your steps, and it's actually quite a funny exercise, if you come up with an answer to something to then go back later and see how did I actually get to that point, if you follow your steps, trace your steps, you would probably find that you did something similar along to this. You did some sort of associative walk on the graph. That makes graphs very natural for representing data, and in particular in those situations where your ultimate customer, your ultimate user, is actually a human being. The impedance mismatch is much, much smaller. So that was number one, the impedance mismatch. The fact that we, at the end of the day, will be interacting with humans when we build systems, and we better come up with a way of doing it in such a way that it's easy for humans to grasp what is going on. There's a second thing going on here, and that is that with problems like contextual information retrieval, we see what ends up happening is that when you look at the different disciplines, so going back to the problem definition, looking at the different disciplines, all of them have their favorite approach to looking at the problem. In artificial intelligence, it's typically about some sort of logical language that you want to represent the problem in. The nice thing about logical language is once you're in a logical language, you have powerful tools like inference, deduction, induction, depending on what your favorite logical language is. And you can use those to arrive at conclusions. If you're more into machine learning, your abstraction tends to be the vector. You want to vectorize everything because once the thing is a vector, you can do pretty much anything to it. You can drop it into your favorite machine learning toolbox and go to town on it. Right? So people tend to have these abstractions that they like to represent data in. Now, with any representation or abstraction, what ends up happening, it's a lossy process, right? When you go from reality to model, when you go from reality to abstraction, you lose something in the process. And that's perfectly acceptable, that's perfectly fine, that's what we have to deal with on a daily basis, as long as the result is still somewhat good enough, right? You want to be close enough to reality so that the analysis that you do and the results that you come up with are still meaningful to the problem that you're trying to solve. So with that, I found that for some problems, the problem is that that abstraction tends to be too loose. It tends to not capture what is the essence of the problem, and in that process, losing the essence and thereby your ability to effectively solve the problem. Now, what is that class of problems? Well, luckily, I went to grad school at a time where a new discipline just emerged, and that discipline is called network science. It was driven by researchers from very many domains, from sociology, biology, computer science. A lot of physicists were in the mix. And they were driven by their desire to understand what seemed to be hopelessly chaotic or complex systems. Right? The study of complex systems had made a great jump since we had the data available to actually analyze them. And they had come up with a range of tools to analyze complex systems. And so I looked at that, and I looked at complex systems, and I thought, that is really interesting. Now, before we look at that, a complex system here is not understood as a complicated system, something that seems chaotic. It's complex in the mathematical sense. A complex system, and I copied that out of a textbook, is made out of many non-identical elements connected by diverse interactions. Now, I think the important part here is many. So you have many elements and interactions. You have many elements that interact with one another. The simplest complex system that I can think of came out of physics. It's called the spin glass model, and is used to model ferromagnets. So if you have a magnet, you know that the magnetism comes out of the little spins on the electron basis. And I'm getting into fishy territory, as you can tell. But the basic idea here is you have these spins, and if you want to model a magnet and understand what state a magnet ends up with, you model it as a spin glass, which is a lattice, a particular type of graph, a regular graph. A lattice is a structured regular graph of individual spins that have a binary state, and the interactions are repulsions between those spins that are opposite to one another. So it's super, super simple. If you think about it, you just have one type of element, a spin, and you have just one type of interaction, which is repulsion in case that the two spins are non-identical. Yet the system itself exhibits very, very complex behavior, and it's extremely difficult to predict the ultimate state that a ferromagnet will end up with. Right? And so it was this class of problems that people became suddenly much more interested in because we had the data available. And the way that people were looking at those problems is by looking at the data. And some of those classes are social networks, or biological systems, as I said, and tried to figure out, can we understand those systems? Now, importantly, the difference here is they weren't trying to force the complex systems into some type of representation that was more amenable to analysis. They took the complex systems as is and went to town with it. And that's something that, as a computer scientist, I was kind of adverse to, right? We don't really like complexity all that much. I mean, we try to avoid it wherever we can. And in the programs that we try to write, we try to get rid of complexity as much as we possibly can. Yet here was a discipline that went out and said, hey, we're going to embrace complexity and really try to make sense of our reality by looking at it as a complex system. To sort of further go into what we mean by complex systems, I think we have some really fascinating examples that we can look at today. One of which are social networks. We now have a lot more data about how humans interact, right? I mean, we have Facebook, for instance, which has, I think, more than 1 billion people now, and a ton of interactions between those people that allow us to study it. But even before that, we had numerous other social networks like the Flickr social network, which is partly available as open source, that we could look at. And we were able to uncover some quite fascinating relationships about society as a whole. For instance, one of the things that we always thought, for many decades, in fact, is that these kinds of networks that arise, and here's a visualization of the Facebook social network, and the arcs indicating friendships between people, that they were pretty random, right? That those were random networks, more or less. The connections between followed a Gaussian distribution, the degree distribution. It turns out, however, that is not the case. And in fact, that networks of all sorts and flavors follow a power law degree distribution. A power law degree distribution, what that means is that when you plot the number of vertices by their degree, that follows a power law, which is a heavy-tailed distribution. You might have seen also, you might have heard the term Zipfian distribution, which is used in NLP quite a lot to model the distribution of words. So that was really interesting that we have these few vertices or nodes in these networks that are highly connected, then a lot of nodes that are loosely connected. But what turns out that is not just a coincidence, because these networks turn out to be extremely robust against interference. If you randomly interfere with such a network, if you randomly pull out nodes, you don't tend to disturb the network very much. Now, why would that matter? Well, it matters for social networks when you look at information diffusion. If you have a society and you want to broadcast information, then it's good that it's robust against these kinds of interferences, because if you have a regime that doesn't like you to broadcast these messages, it makes it harder for that regime to interfere with your activities. It's also interesting for the internet that we all rely on. It actually follows that very same distribution, which is kind of funny, right? If you think about it, you have a social network on the one hand, you have the internet on the other hand, yet at the core, if you mathematically take it apart, they look very similar. They also have that robustness built in given by the power law distribution, which is good for the internet because it means if I take out a random server, it doesn't disrupt the internet all that much. And in fact, you probably won't even notice. So we have the internet as a complex system, social networks as a complex system that we can analyze. Biology is another fascinating area where complex systems are becoming much, much more important as we move on. Because as we study the human system, it's one of the most fascinating complex systems you can think of, right? We're all made out of individual cells, right? Those are like teeny tiny. If I put them on a table in a cell, you couldn't possibly imagine that you could build a human out of that thing, right? You take billions and billions of those, put them together, and suddenly, bam, here comes a human, which is called a phenomenon that is called emergence. When you have many systems that, when put together by way of their complex interactions, exhibit a new behavior, that phenomenon is called emergence. And it's something that is unique to complex systems and something that I think is quite fascinating. Because if we try to avoid complexity where we can, what we essentially end up doing is we avoid emergence. We avoid the phenomenon of emergence. Emergence that also happens in social networks. If you look at the Arab Spring, for example, there's some indication that Twitter played a role in that, which is a role that emerged on top of that communication platform that they built, probably not foreseeing that it could ever have that impact. Biological systems are no different in that. If we look at the human body, most of the diseases that we're faced with today can no longer be easily solved by developing a drug that just targets one particular spot in your body. If you look, for instance, at cancer, if you look at HIV, those are highly diverse diseases that require a holistic system analysis in order to understand how to tackle them. And that, in turn, requires us to analyze and understand complex systems. And lastly, the financial system. I think we've had a very vivid demonstration of what happens when you don't understand complex systems. That happened in 2009 when the financial system was on the brink of collapse and nobody really had a clue what the hell was going on. The reason that was the case is because we did not, and at that time, didn't try to understand the complexities of these different financial dependencies between the institutions, and therefore had no idea what was going to happen when one of those collapsed. Again, pointing to the fact that complex systems are extremely important for us to understand and analyze, and while we try to get away from complexity where we can, I think a much more interesting approach is now to actually embrace it where we find it so that we can exploit it and build really cool systems and solve really cool problems in the process. So putting the two together, I got really interested into enabling humans to analyze complex systems. By the very nature, that is, they're complex. So we need good tools in the process to give humans the power to actually look into them and make and derive conclusions. How would we fight a particular disease? How can we structure our society so people are happier? How can we build our financial systems so that they're not so volatile? All these questions, I think, are eminently important, and they can only be solved if we look at the complex systems that underlie them. Now, the thing is, though, we don't really have a whole lot of good tools, right? We don't have a lot of good tools to analyze these complex systems, and that's why we went down the journey of building some. And that is called, one of the tools I want to talk about is called Titan, which is a distributed graph database. It's part of a larger stack called the Aurelius Graph Cluster. And what we're trying to do is we're trying to build a holistic ecosystem of tools that allow you to tackle these types of problems. As I've hopefully managed to do by now is to at least convince you somewhat that graphs are really useful, one, for representing information in a way that is natural for humans, but two, also to represent complex systems. Because by their very nature, we have many elements that interact by a set of diverse interactions, which is exactly what a graph is good at representing. Right? So graphs seem to be a fundamentally important data structure. I don't think they're given a lot of, think they're given a big role in our education, but I hope that that is going to change. And if you take anything away from this talk, and ignoring anything I'm going to say later, is really that point of graphs, looking at graphs, and trying to figure out if graphs could become part of your day-to-day toolbox. I think if we want to solve these problems, graphs need to become as natural to us as hash maps. We use hash maps on a daily basis. We don't really think much about them. We know when to use them and what they're good for. For graphs, that is not so easy, maybe just because we're not familiar with them, but hopefully we'll get to that point, and you will be able to use them just like you currently use a hash map. Now, one particular implementation of this hash map or particular implementation of a graph is Titan here. There are many others, and I encourage you to check them out, but I'm going to talk a little more about Titan and the distributed graph database. Titan itself is inspired a great deal by the most amazing graph computer that I know of, and that is the human brain, right? It's the only graph computer that we know of that actually natively runs on hardware that is amenable to graph computing. So we're kind of at a disadvantage as computer scientists trying to build a graph-based system because our hardware is essentially sequential, right? We're still very close to the original Turing machine. Instead, we have this one big long tape. Now the tape is partly in the level caches, partly in RAM, and partly on disk, but it's still pretty much sequential and doesn't have that connectedness property that our brain has. But still, I think we can make a good attempt at that, and with Titan, we're trying to do that. Titan partly tries to get around that problem of sequentiality that our von Neumann architecture imposes on us, but representing graphs in an adjacency list format. But there are three things that really differentiate Titan from other systems that I know of that are inspired by how the brain works. I want to talk about these three. The first is our brain is a highly concurrent distributed system. It's quite amazing how that works. We're not consciously aware of it, which is even more amazing, but at any point in time, you have many, many processes that concurrently happen in your brain, and while most of your brain is effectively at sleep, meaning not literally sleeping, but not active, right? And so in building a graph database, we felt like one of the things that we needed to build in from the get-go was that ability to be highly concurrent and highly distributed. Now, we benefited greatly here from the event of NoSQL, which was really concerned with building distributed architectures that were fundamentally scalable, so we just piggybacked on top of that using Cassandra, Apache Cassandra and Apache HBase to build Titan on top of. But there are some unique challenges to building graph database, and one is that it's not quite so trivial how you want to partition your data. How would you assign a graph to the individual machines in a cluster? right? How do you coerce a graph into rows and columns, which is ultimately the big table data model that you have? Now, we said we're going to use a adjacency list representation. That's one thing, but it still doesn't answer the question for how do you assign the individual vertices to individual machines. That is a problem that is called graph partitioning, and it's quite amazing how our brain does that. It was long thought that the different parts of our brain was sort of had fixed assignment, that there was this motor brain and that there was the visual cortex, and that basically that's how it went, right? That's how the brain, by your genetic code, would ever represent, it's ever allocate its computing resources. Now, it turned out, though, that when people looked at blind people, that it's not true that their visual cortex was just sitting there not doing anything because, obviously, since they were blind, it didn't have any input. It actually turned out that the brain reallocated those computing resources to other sensory systems, and therefore blind people have much better senses when it comes, for instance, to touch or smell. Now that is quite fascinating. How does the brain do that? It seems to indicate that we don't have genetically encoded the way that the brain partitions its resources, but that there's some way of figuring out. And in other words, that's something that we needed to do with Titan as well, is some way of figuring out how to allocate the particular machine resources to particular parts of the graph such that we still balance out overall the computational resources so that we don't have hotspots in our system. Now, it's a problem that by no means I'm claiming to have solved because it's quite challenging to do when you have a real-time system that receives updates all the time, right? You never have a static view of the graph that you can then go to town on and say, I'm going to cut this up in this way and then store it on these machines. So the approach that we take is a mixture of existing partitioning algorithms, and we have used label propagation most effectively to solve that problem, but combine it with an innate understanding of how the graph works at the data model and allow Titan to give it hints so that it knows how to chunk up its data and then use automatic methods like label propagation to fine-tune the partitioning. And we found that to be a very effective solution to solving this problem, and just hope to do much more research along those lines to come up with brain-inspired partitioning algorithms. Another thing that our brain does quite amazingly well is figuring out what is relevant or not. I mean, at any given second, you're bombarded with tons of information, and our brain seems to filter them out pretty well so that you focus on the most relevant ones. More amazingly, even though you might temporarily consume a lot of information, over time, it seems that only the most relevant stuff survives. If you look at neuroscience, people say, well, the things that fire together wire together, so the things that you frequently use get connected, and the connection gets stronger over time as you use them. And that's, I think, a very important principle. But there's also this principle of weighing or relevance. Or as Jeff Hawkins wrote in his book, the brain has a strong sense of sequence, of time sequence. Time is a very important dimension for us humans. We think of things as they occur sequentially over time, but we tend to order a lot of other things as well. So that notion of ordering in a graph is important, and one way that Titan incorporates that is by the notion of a vertex-centric index. Now, what does that mean? When you look at a vertex in the graph, you have all these incoming and outgoing edges that connect to us, as shown in this picture here. Now, typically, typically the way they would represent them is you look at all edges and create them equal, right? And so then when you retrieve it, you have to go over all these edges. They're all equal, so you have to iterate over them and then figure out which of these edges are actually meaningful to you. What Titan allows you to do, it allows you to specify certain relevance criterion by which you want to order those edges and then index them accordingly so that you can say things like, give me the edges that have the 10 edges that have the highest timestamp. Time, again, being a very important dimension here by which you would order those edges. Right? And Titan will then lay out the data in the underlying storage backend so that it can efficiently retrieve only those edges that you're actually asking for. Right? Another way in which we enable, or in which we build Titan that is inspired by the brain, and it turns out that is fundamentally important when you look at scalable systems, because as the amount of data increases, each vertex, the degree of each vertex, meaning the number of edges, also increases. And so you quickly run out of space and out of computational resources, and things just slow down a lot if you don't have these index structures. And finally, one of the things that our brain does amazingly well as well is that subconscious thinking. Now, you think when you sleep, your brain is asleep. That turns out to be false. In fact, our brain is anything but asleep when we sleep. It does a very important job, and that is organizing our brain. You receive a lot of information during the day, and at night, your brain goes to town on that information, trying to sort it into what you already know in order to make sense of your world. What I'm trying to do today really is to implant in you that idea that graphs are important so that when you go to sleep tonight, it's going to subconsciously eat you up from the inside, and then you wake up tomorrow and you're like, man, I should learn more about graphs. That's really what this talk is all about. But that notion of real-time processing, which we all are aware of, that's our day-to-day thinking, that's how we go about the world, but also the subconscious, the lingering thought, I think is a very important analogy for computing as well. We have Titan, which is a real-time system. It answers real-time queries that you have for your day-to-day applications or operations. But then we also built Faunus, which is in a way Titan's brother and responsible for analytic type processing, the type of lingering thought when you try to analyze or rearrange your data. It operates directly on Titan and in fact uses the same query language, Gremlin, that I showed you. So the way that you think about the data is the same, but the process behind it is different. One is real-time, the other is batch. One is OLTP, the other is OLAP. But both of them are married together in an approach that is tightly integrated. You don't see any ETL pipeline going on here, right? So the important aspect here being putting those two together so you can build applications that take advantage of both your real-time thinking, but also that lingering thought, the analytics, what drives a lot of the analytics processing, and marry them in one coherent system. So that basically concludes the rough overview of Titan and Faunus. All of this is released as Apache 2, so you're happy to check it out and play around with it. It's still very young. We're actively developing on it. There are lots and lots of very interesting questions that are still open and not solved. And we would very much appreciate any input from the community or any help you want to offer here to build those. I think it's a fascinating area. There are lots of really cool questions that you can solve or address with this. And I hope you get the time to check them out. Thank you.